Moving a pi bond can be done by addition followed by elimination. In this case, we put our bromine in the more substituted position, so that's a Markovnikov addition, and the reagent would be HBr. You can see for the elimination step, we made the less substituted alkene, so that's a Hoffman elimination. The reagent that we would need there is t-BuOK. Now, there is another way that we can move this pi bond. Right now, we've made the least substituted alkene from the most. Right, we've gone from tri-substituted to di-substituted on one side. But we could also go from tri-substituted to di-substituted on two sides. Let me show you what I mean. Initially, we started out with Markovnikov hydrobromination. So let's start this time with anti-Markovnikov hydrobromination. The reagent we'll use is HBr with ROOR, peroxide. And our product is the less substituted alkyl bromide. If we then do a Hoffman elimination, we'll end up with a di-substituted alkene, but not the di-substituted alkene we initially got. There are two different beta positions where we can do proton transfer, so those are the beta protons available. But using this very bulky base, the t-BuOK, we're going to go after the less protected beta protons here. So here's the base attacking the proton. Those two arrows constitute proton transfer, and then we get loss of a leaving group. And in our alkene product, we have moved the pi bond in the opposite direction. Of course, we can't do substitution, elimination, or addition unless we have functional groups or pi bonds. So the way to get a functional group and then a pi bond in there is to start off with radical bromination. And we use bromination because that gives us the most regiochemical control. It'll always favor the most substituted alkyl halide. If we did radical chlorination, we'd get a whole bunch of different products with the chlorine at all positions around the ring. If we then treat our alkyl bromide with sodium ethoxide, that'll give us a Zaitsev elimination to give us the tri-substituted alkene. If we use a bulky base, t-BuOK, instead of sodium ethoxide, that gives us the Hoffman product, which is, in this case, a di-substituted alkene. If I want to go from an alkane, like 2-methylbutane, to an alkyne, like 3-methylbut1-ine, well, first I'm going to have to do radical halogenation. This will give me 2-bromo-2-methylbutane. If I then do a Zaitsev elimination using something like sodium methoxide or sodium ethoxide or sodium hydroxide, I end up with 2-methyl-2-butene. I use HBr and peroxide to do anti-Markovnikov hydrobromination, and I get 2-bromo-3-methylbutane. We're getting closer. Next step is going to be a Hoffman elimination. So I do this using t-BuOK as my base, and it takes the least substituted beta proton to give me 3-methyl-but1-ene. Halogenation of my 3-methyl-but1-ene using Br2 in CCl4 gives me 1,2-dibromo-3-methylbutane. Reacting this with excess sodium amide does a double elimination to give me the alkyne, and then goes further to make sodium alkynide, which precipitates out. I then work it up with water to maximize my yield. and I've got my product. It only took 1, 2, 3, 4, 5, 6, 7 steps. Can you do that? Now you can.